Hello everyone. I hope you can hear me. I will wait for the okay, all clear. 1 2 1 2. Yes, so we don't have the same problem we had last week, where for some reason my microphone wasn't picking up any sound. So again, welcome everyone. I'm Andrew. I will just take my notes here. All right. So, quick introduction. I'm a student at the university in master degrees in electrical engineering. In fact, I'm more of a software computer sorry. I'm more about computer science, but in the province of Quebec, there is no computer science engineering master. So the real name is electrical. I'm interested in designing ICs, so it's very low level. And for the past 2 weeks, I've been enjoying Twitch and giving you some concept about FPGAs, stuff that usually people don't really bump into when they start programming. It's a different beast than CPUs and GPUs. So last week there were a lot of people in the relative to what I'm used to who asked question about different kind of but how can we run or simulate a CPU such as a RISC-V on an FPGA. And I have I found some examples, so let me get them for you real quick. Oh, damn, confirm. Okay, so right over here, it won't be too long to make sure I have the right run. Okay, so here also you can hear my cat meowing. He just threw a fur ball like 20 minutes before a stream, so we gave him some medicine. He might be a little excited. So the Bonfire processor is a RISC-V based soft-core processor. So soft-core, what you need to know is that it's a CPU that is developed in HLS, so high-level synthesis. So it's usually C or C++ application that are converted into circuits. So there are some limitation. Obviously, you can do all of what like C or C++ gives you, but you can easily really create how the CPU works at the gate level. They can also be developed in other languages. I think this one is in a certain, how can I say, not a taste, but a flavor of Lua. But there are other with that uses Verilog or VHDL. VHDL is the language I'm currently using from the past two streams. And so those can be run on fairly, how can I say, modest FPGAs. So if I go down here, sorry, we can, I think we can see where the, what kind of system they tested it. So no, it's not this. Maybe it's not that project. Sorry, I will get the other one. 1 second. I will just put this back here. Going there. Okay, so there were this one. Okay, this one was very interesting. In fact, it's a. I won't play it. It's a YouTube video that explained how these guys made a RISC. In fact, it's 8 RISC-V cores on a $38 FPGA. So for those who saw this last week, this is the FPGA I'm using. It's a Arty Z7 that runs in ZenQ Z7-20. So it's not the smallest, it's not the biggest, but it has some good feature. But this board costs about $400 Canadian dollar. What they claim here is they can run 8 RISC-IV cores on a $38 FPGA. How they do it, however, is very clever and interesting. They use techniques. They use a lot of techniques, but one of them is that they operate bit by bit. So those RISC-V core are really slow. If they run Linux, they won't be usable. All right. So it's very for poking the technology and trying RISC-V in a really humble way. So these guys made this, and there were another one that I found. So this one, what was per? This one has something interesting. What was it? I didn't take it. Oh yeah. Okay. So it can be compiled with various settings. So for instance, this one only has the RV32i. So if you are familiar with RISC-V, they have a bunch of extension that can be not activated but implemented, and there is the I, the A, the Z. There's a lot of different options you can activate, and there is some other feature that can be added or not. So no data bypass, no interrupt. Now in that you don't have data pass bypass, but probably as interrupt activated, and there's a lot of other. Here we can see that this one has the I extension and the M extension, etc. IMA here, some information in the benchmark they made, and those are FPGA that they are using. And the FPGA that you saw earlier, the ZenQ, inside the ZenQ there is a Arty 7. Okay, so if we look here, Arty 7, those are Xilinx, and if you look at Cyclone 5 and 4, sorry, those are Altera. So you know, Altera has been bought by Intel some times ago. There were some story around changing the naming scheme. So they use Intel, and there were confusion. People didn't really like it, so they came back to Altera. Xilinx was bought pretty recently. I think it's like 2 years ago by AMD in response to Intel, and Xilinx can be seen here and there, but a lot of the documentation and information that was used to be on Xilinx.com is now on AMD. And if we look here, so we can run this how can I say, this version of the RISC-V implementation from Vex RISC-V project that implemented the RV32 extension I and M that has caching. So MMU, first of all, MMU means it has a module that gives some functionality for memory management. So it's called a memory management unit, and this, for example, can help create different channels to communicate on different how can I say, devices. All right, and they successfully make it run at 151 megahertz using 2021 LUT. So LUT, don't forget, they are lookup tables, and FF means flip-flop, so 1541 flip-flops. If we go back on the website digilant.com and go find if we go find our card, so FPGA board, all system, we can, this one here, Z7-20, and we go to feature. So logic cells, we have 85,000 logic cell, each of which has different amount of LUT and flip-flop. So this this one here has the potential to be running this core. So for those who were skeptical, you can now be happy to know that we can run those kind of machine on an FPGA. And if you are interested in the one that uses like 1 bit operation at a time, go watch the video. I will link those websites on my GitHub. All right. Okay, so I will do a little recap of last week. Last week we work a lot on the UART, TX and RX. So TX is transmission, RX is reception or receiver, transmitter receiver. So I wanted to be able to communicate with the CPU inside the FPGA. Okay, so if I go back here, this little ENQ, it's not only a FPGA. It has what is called a FPGA fabric, the component that gives me the opportunity to design any circuit I want. But they packaged it with 2 ARM CPUs. So 2 ARM cores. They are clocked at 650 megahertz, and they are 32 bits CPU. So the architecture is I don't remember which one. We can go real quick back to the page. Sorry about. I closed it. Sorry. I will open again. Digilant. So if I go back to my board here and here. Okay, let me show you. So if I go back here and I go to feature, I guess I will see it's Cortex A9. So going here, ARM Cortex A9, we will see that it's a 32-bit multi-core processor, up to 4 cache coherent cores. Like I said, the current FPGA that I use only has 2 on the ARM V7 architecture. So it's pretty old for an actually pretty old. There is V8 and V9, but I think V8 is 64-bit, so it's probably the last-ish 32-bit architecture. And now you have V8, V8.1, 0.2, and V9 I think just got out there recently. If I'm correct, I think only the I correctly if I'm no, the M4 is V9. I'm not sure if Samsung is it Samsung or Qualcomm, the I don't remember the name. Let me see here. Snapdragon X Elite. Is it Samsung or Qualcomm? Yeah, it's Qualcomm. So is it a V9 or a V8? No. Sorry. Too fast. Put it there. Go back. Snapdragon X Elite. can I see this easily? It's a 64-bit core, 12 cores up to 3 points single core, blah blah blah. Memory storage. Okay, so let's ask Google which ARM architecture is the Snapdragon X Elite. It's ARM 6. Yeah, doesn't let me. I can find the information quickly, but I'm not sure, but it might be V9 or V8. But it's surely 64-bit. All right, okay, let's move on. So let me just replace this. Okay, now, so we work on this to make sure we could communicate with the CPU and make it work, and in that manner we achieve one important test: does the system works? Because in order to access the CPU, we need to configure the FPGA fabric to activate them. So everything on that chip is activated and controlled by the FPGA fabric. So for those who didn't see, we have what is called a block design that we've created. And where it is now. Okay, so this block design is the minimal block design we need to access the CPU. So this is actually the representation of the CPU. If I double click on this, and by the way, I'm using Vivado 23.2. If I double click on this, I can see the block diagram of the ZinQ. So those are all components I can activate around the CPU. We say CPU, but in reality it's like a SoC. Because there's a lot of other components in there. So we have the CPUs, we have an application processor unit that has a lot of cache and other utility that communicate with the how can I say, the external world for the FPGA. And we have some modules to communicate on the EXE bus. We might have time today to use the EXE bus, but I doubt it. It might be a little too much, but probably next stream we will go there. Now we have a lot of peripherals. So SPI is a communication protocol that has some advantage. One of them is that it is full duplex. Full duplex means I can send and receive data at the same time. On the other hand, oh, hi, Twitchy Soul. Welcome to the stream. So SPI is a protocol that gives the opportunity to communicate in both ways at the same time, contrary to I2C, this one, which is more comparable of a network, like RH245, for example. Now, CAN is usually a really resilient network. It's not really made for high throughput data. It's mainly used on cars and stuff like that. It can withstand a lot of noises. UART, that is what we use the past to stream. So UART is like the basis of what was the COM port back in the 80s, and it's also the basis on how USB works. So USB is built on top of UART. GPIOs, the name just means general purpose input output. So they are just inputs and or outputs I can configure as I wish. I think the SD is for SD card, but I don't know why I have two. I think I just have one on the board. Let me see. It's hidden in the back somewhere here. Yeah. So this is my SD card. Maybe I have other connector I can activate. I don't know. In fact, if there's other stuff in there. USB, so USB 0 and 1, Ethernet, those are Ethernet, I suppose. And there's other connection. I don't know if you remember, if you were there or not, the FPGA, the FPGA fabric doesn't have, is not permanent. So if I program it for something and then I turn it off, unfortunately, the program that was on the FPGA will disappear. So those here, flash memory interface, so SRAM NOR, NAND, or Quad SPI, those are there to keep the program in memory. It's like my SD card or my NVMe, for instance. And when I start the FPGA, it will program the board. I mean, it will program the FPGA with the program I left on that device. So I need one of those three. Right now, I'm in USB mode or GTAG mode, so I can program and run it, debug it while I'm working with it. But at some point, I will need to like use this device on like a project. I will program this device, and in that context, it will be the Quad SPI. Good. And there's a lot of other stuff we can see here. We can configure a lot of AXE things here. We won't be talking about that today. This is the place we worked last week and the first week also. So my UART connection is connected on pin 14 and 15 here. I could have programmed it anywhere, but I have to have access to those pins on the board. And the manufacturer, the Gilent, who made the Arty Z7, has connected those there. And it's pretty much what I use. I think the USB is connected. Let me see. Yeah, here. And you can look at the top. So my FPGA has two banks. One is set to 3.3 volt. The other one is set to 1.8. And these are configurable as what I need. So, hi Sparkling Mango, and welcome Calendar Hero. All right, okay. So, and one of the things I showed last week is we have the clock configuration. The DDR, we won't be touching it for now. It will be I'll go there down the line. So here we can see that those two CPUs, like we saw on the schematic here, those two CPUs are clocked at 650. I can crank it to 677. It won't be that much of a jump. But I guess the reason why it's 650, it's the binning of that FPGA. They can assure me it will work at 650, but they cannot, like it's not certified maybe for 677. And I might be able to run it at that clock, but for like 17 megahertz, I won't bother. And the DDR is clocked at 525 megahertz. And there's other, I can create other, where they are, is it here? Yeah, I can add or remove personal clock I will use on my designs. We might go there today. Like I said, last week we did the half adder. Today we will do the full adder and a 16-bit adder. So it can be used in a naive 8x8 multiplier. All right. So the goal here is really simple. I want to introduce a concept. So last week we did the adder. So if I go back there, sorry, here. Okay. So we did a half adder. I will go to the board soon, but what happened here is these are like the lines of code that are being executed when I use that entity. So we can imagine that, for instance, I will go back here. Oh, I think it's disconnected. Start broadcast. Sorry. I will go back here. Connecting. Is it? Yeah, okay. I will go here. Perfect. Okay. So let me just move my microphone near the. Okay. So what we did essentially is a half adder. Here, half adder. So if we have like a signal A that is 1 bit, a signal B that is 1 bit, I want to know what is the sum of those 2 bits and is there any carry. So like for instance, we said that if I have 0 plus 0 we equals 0, 0 plus 1, or the inverse is 1, but if I have 1 plus 1 we have 0 carry 1, and we want to know is there any carry on our addition. So what we found out is if I have A and B like so, and we want to look at the sum. So sum, these are the values we have at the bottom here. Sorry. So when we have 0, 0, it's 0. When we have 0, 1, 1, 0, it's 1. And if we have both, it's 0. Okay, so we learned that this truth table, it's a XOR. All right. Now the carry, we have A, B, and the carry C. 0, 0, 1, 1, 0, 1, 0, 1. So we have no carry for the first 3 and a 1 at the last possible combination, 1, 1. So this is called an AND. The AND gate tells us that like the way I like to explain it is if both of my signals are 1, this is the only way to have a 1. So to have a 1 in an AND gate, all of the input needs to be 1. It's in contrast of the OR gate, AB, 0, 0, 1, 1, 0, 1, 0, 1, where the only way to have 0 is that both input are 0. Okay, so they're like there's a little bit of there's a kind of a mirror effect, or I don't know how to explain it. You'll see further down the line if we go there that this is the basis of the De Morgan rules or laws, where you can express the same expression in a different way. All right. So what we see here is that our adder, F adder, if I have A and B, so the sum it's a XOR that is represented by this little symbol here. So here is the sum, and the end, this is the symbol. We have A and we have B and we have the carry there. All right. So that's what we saw last week. And one of the things I need you to really understand is this here will be executed at the same time. So it's not like in your C program where you have C equal A plus B, D equals A times B, and those are sequentially executed. No. In the FPGA, when I explicitly write those line of code in that way, what it means is I create a circuit that takes A and B and create the XOR gates and connect that output to the S variable. Same thing with the C. We take an AND gate, we put A and B there, and like electrically connect to C. So those two lines of code are, for all intent and purposes, executed at the same time. Okay. So this is one of the first things that will be hard to understand and like to grasp when we go from conventional sequential programming to VHDL or Verilog, stuff like that. And when we have a circuit that doesn't have any state or doesn't have any condition or any process that can like hang what we will see in the future when it has a clock or not. So this is called a combinatory circuit. All right. And today we will try to go and create a multiplier, a naive one, something that will be very probably not very efficient, but then we will start doing sequential circuit. Okay. So today we will go back to the half adder and try to figure a way to create a full adder, and then with that full adder create a 16-bit full adder. So instead of adding only one bit, we can have up to 16 bits that are added to two variable A and B as 16-bit both, and it will be our starting point for our multiplier. Okay. Nice. Thanks for the follow, guys. Really appreciated. So let's go back to the drawing board, shall we? Okay. So one of the thing that is one of the problem we have right now is that I cannot use the half adder in a way to add a lot of bits that are together. And if I go back on how to count, you remember that if I count in decimal, I have 10 symbols. So 5, 6, 7, 8, 9. When I'm at the last symbol available, what I do, but I realize that on the left side there is a 0 that is implied. So when I'm at the end of I use all the symbol I have, I add 1 to the left and start over. All right, and we go there ad infinitum. If I'm in binary, it's very quick because I have 2 symbols. So now I have 0, 1. I want to write 2, but there's no 2. So what I do, I add 1 to the left, start over. 3, 4, 5, etc. All right. And we saw also that if I want to add, like, I don't know, 5 plus 5, what I do is I will use the same way I would do 1 plus 1, it's 0 carry 1. 1 plus 0 is 1. 1 plus 1 is 0 carry 1, 1. So I have 1, 0, 1, 0, and I can assure you that this is 10. Okay, 10, 10 is 10. That's pretty easy. And in hexadecimal, it's the letter A. So what I want, in fact, is that my half adder only has 2 inputs. So I can do that part. But I cannot do this here. When I have a carry that overflow, I would like to acknowledge its existence and compute it. Okay? So what I need is a adder that has A and B, but has a C in, so a carry in, and will output a sum and a carry out. Okay, C out. And to not be confused with the C out in C++, it's very, in that context, is carry out. Okay, so now we could go back and draw the truth table, and what we will realize is that if I have A, B, and C, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. All right. So this is Cn. So let's see what's going on with sum. Okay, so the sum is what I want to go at this place, and the carry are here. Okay, so Those are the carries. Those are the sum. So if I have L0, obviously it will be 0. I have 1, 1, it will be 1. And I have 1, 1 here too. If I have two ones, it's a 0. So here 0, 0, 0. But if I have 3 ones, but of course I have a 1, 2. Okay. Now, what we will realize is, in fact, the A, usually at the start we add A XOR B equal S. If I look carefully to this and the output here, what we will realize and we could prove is that A XOR B XOR C in is S. And the way we can see it is that if you look here, here, this is the definition of a XOR. So we have the same truth table than we had earlier in that page here. Okay, the same thing here. Now, this one is all zeros, so when I add a 1 here, we can like imagine that this will produce the same value here, but XOR with another 1 here. So if I have 1 XOR 0, it's 1. If I have 1 XOR 1, it's 0. 1 XOR 1 is 0, and 1 XOR 0, it's 1. So we really have A XOR B XOR C in. Good. Now, let's look at the carry, and what we will discover is that it's a little bit more complicated, and we will introduce the Carnot table. Carnot, I think it's like that. Sorry, there might be a T somewhere. Table. Okay. So before doing the Carnot table, we will do the truth table. So let's move this over there and start the C out. So the C out will be 1 when there is at least 2 or 3 ones. So we have a 1 over here. We have a 1 here and here, sorry. And we have 0 everywhere else. So when we look at this, we see that this is an AND and this is an OR. But it's not clear how we can connect all of these in that context. So what can we do? It's the Carnot table. So the Carnot table will be over there. How do we do a Carnot table when there are 3 inputs? I will ask you to try to follow the concept for now. There will be a lot of information that will be thrown at you. If you have any question, don't hesitate to ask them. But you will transform this table that is one-dimensional into a 2D table. So we have A, B, and C out. We could have put just A there and B, C out here. Doesn't really matter at the end, but there are some rules we need to follow at considering if there is only 1 or 2 variables. So here, C out can have the value 1, 0. AB can either be 0, 0, 0, 1. And now we will use what is called a grayscale. I think it's grayscale. I don't remember. I think the term gray is there. So the next one we would want to put 1, 0, but it's not the value we need to put. The way we need to do a Carnot table is at each steps only one value needs to change. We cannot change both. So if I put 1, 0 here, this value has changed and this value has changed, and it's not what we want. You will see why in a second. What we want, we want to change only this one. If I change this, I go back to 0, 0, and this is bad. So I can only change this one. So 1, 0, 1, 1, sorry. and then 1 0. Okay. This method of encoding has been used, for example, in for instance, how we encode the sector in hard drive. So, like a magnetic hard drives, there is a spinning disk, and there is encoder to know where in the disk we are, and those encoder usually use a grayscale encoding like this. So if the disk turn and more than one bit change in the encoder, the disk detect the problem. All right. So what happens if both A and B are 0, but and Cn is 0, but we look at the table here, we have a 0. So we put 0 here. And if I have a 1, I put 0 here. Sorry. So I did those two here. Those 2 bits, I put them there. Okay. So now 0, 1. So 0, 0, 1 here. 0, 1. We will have 0, 1 like that. So you have 0, 1. Okay. Now 1, 1. We will look at those 2 lines here. Sorry, I had diversion. I was distracted. Okay, so if we look at Cout in both ways, either there is only AB or ABC in that as 1, we have a Cout that's 1. And 1, 0, we will look up at those 2 lines here. And what we see is that if C1, Cn is 0, we have 0. Cn is 1, we have 1. So we have 0, 1. Okay. So now what can we do with this? So what we can do is group these in a packet of 1 by 1, 2 by 1, 2 by 2, and all group we can make. So I can, for instance, group these 2 here. Okay. Why I cannot group all of those 3 here? The problem with using these 3 is that the group needs to have a power of 2 element. So 3 is not a power of 2. I can circle only 1, 2, 4, or 4, 8, etc. Okay, so I need to group by power of 2. So one way we could look at this is group this 2 there, group these 2 there, and group those 2 there here. Okay. So how do I extract an equation with this? Okay, so the goal here is to use AND, OR, XOR, stuff like that. So let's take those 2 value here. Those are really simple. What it tells us is that A and B won't change. So A and B are 1. And if R and B are 1, it doesn't matter what the value of Cout is, we have a 1. Okay, so if A and B is 1, the output is 1, and we don't care about Cout. Okay, so how can we write this? We can write A and B. You remember we could put a little dot here to express the AND, but usually what we will do is just bring those 2 letters together. So since I didn't do everything, I just did 2 possibility of all the 4 ones I have. So how can I add other? But I need to look at those 2 here. Okay, so if I look at those 2 here, what it says is that it doesn't matter if A and Cout are 1, it doesn't matter what B is. B can be either 1 or 0. Okay, so those 2 here, I will draw them in pink, those two here, plus a C out. Whoops. Okay. And I will rewrite AB in blue so we can have a... Okay. So you will probably say, yeah, but Andrew, this one here, you circle it twice. It doesn't really matter, because at the end of the day, what it means is that this expression and this expression might be true, but at the end of the day, since it's an OR, it will return true, and this is what we want. All right. And if I would say, for instance, I will do something that I don't recommend. I will just take this one by itself. Okay. So if I circle only one, what will happen? Let's change this color for orange. If I only just take this one, now I need to tell, how can I be sure that A is 0, B is 1, and C out sorry C out is 1. So this adds a little bit of complexity for no reason. Okay, because at the end of the day, if I go back, so like this, and I use here those two ones, what happens? We realize that B and C out are ones, and it doesn't matter what A is. So we have the equation B C out with a plus here. Okay, so this gives me the equation to be able to compute the C out. Okay, but what we will do today is, will be a little different. We will use 2 half adder. Okay, so let's make a big box here, and inside that big box we will create 2 half adder and half adder. So let's start easy. We have A, we have B, we have C in. Okay, if I put A and B in here, S here goes into the A of this one. So this is the A, this is A and B. We will call them 0, 0, 1, 1, 2, and B2. Okay, so what do we have here in that signal? We have A0 XOR B0, or in fact 1, 1, but you see my point. Okay, now I take the C in here and put in the B1 here, B2. What do we have at the end? A1 XOR B1 XOR C in. So this is our sum. Everything's worked fine. Now we have the carry here. We will have the carry here. And what is the output of this? Okay, so just a second. So if I have a carry here, what does it mean? It means that I have 2 ones here. So I have a carry to at the output. Whoops, sorry. I dropped my pen. Okay. Let's clean this up. If this one is activated, so there is a carry, this one and this one are 1. Okay? So if this one is 1 and or this one is 1, I want the carry to be on. So it's an OR that goes there. So let's draw a OR, and don't forget that sorry, 2 seconds. 2 seconds. Okay, sorry about that. I have some difficulties to say the word or. Okay, let's go back again. Don't forget that the XOR, there is a like a floating thingy there that the OR doesn't have. So this is a OR, and the C out is the equation, this signal here, or this signal here. All right. So this is what we want to do today for now, and after that we can use this construction, chain those together. So A0, B0, C in 0, and this is S0, C out 0, connect to the C in here, A1, B1, S1, like that, and goes the 16-bit adder. Okay? So let's do this. And we will also do some test bench also. Okay. Perfect. So now we will create a new source. So we go here, create a design source, create a file. It will be called the full adder. And finished. Now the full adder as A, B, whoops, and C in. Okay, and we have the sum and cout. Those are output, like this. So these are not buses. We say OK. It will create the full adder, and now we are ready to make our code. And this is something we didn't do. We will do something new. We will use an entity that we've created, so the F adder. We will like instantiate it, so like a class in C++, and connect all the wires we need to connect. Good. So I like to separate this. So in fact, I'm not really like, I have a certain way to code in VHDL. Usually I will like put my input like that. I won't be using this kind of notation for naming. Like A, it's not really a good name for this. C and all. Well, CN, it can be used in that context, but for now the goal is just to keep it simple, and with the schematics it will be easier to follow A, B, C in, since it's easier to write. Okay. So now one of the things I really don't like, and I talk about it in my previous week, when we did the benchmark. So I don't know if you remember this. Last week, what I said is that it's really cumbersome in VHDL. We need to copy the entity in the test bench. So like in C++, if I create a class, I won't need to redefine the class in another class that uses that class. Okay? But in VHDL, you have to. So it's like like VHDL is very old. I think it's older than Verilog, but this is something we have to deal with. So I will just take this component here and copy in this section over there, and just so it's a little bit more beautiful, let's make it more beautiful like this. I don't know why it always does that here, and like such. One of the things that I really don't like also with the VHDL is that it's very confusing when you start. So here's the list of the input output of your component, and you have the same thing here. You have the input output of your entity over there, and the last one on the list must not have a semicolon. Okay, you must not put a semicolon over there. What you have to do is close the bracket and then put your semicolon there. Okay, so sometimes you go fast and like, oh, I need another output, like let's say I don't know, the product out std logic, and it's a mess. Like you don't, it's something that happens really often. You forget to put a semicolon before because you add something after. It's like it's the same thing as when you start doing C or C++ and you forget your semicolon. Now is like the next level. You forget that you had to put one before. It's annoying. Okay. So now I will be able to instantiate my half adder. But if I go back to my drawing session here, there is two things I need to create. Okay, so I will need to map to this first one, A0, B0, and I will need something that will represent the output and make the connection between my first adder and my last adder. This is called a signal. Okay, and I will need a signal over here and a signal over here. Okay, so I will create those signals. We will call, so my signals, I can put them here or at the top of the component, doesn't really matter. So the first one will be signal A, X, or B. So this is the output of the first half adder. It will be a std logic. And I know I didn't explain what std logic refers to. You can represent it by a wire or a port. So here they can be considered ports that connects to the internals of the entity. And here they are wire that I will connect on different elements. Okay, I will need the first carry, the carry of the first half adder, and I will need the second carry of the first adder. So signal S carry 1 and signal S carry 2, like such. And remember that in that context here, when I define ports in my component or my entity, I need to not put a semicolon here, but when I define signals, all of those signals needs their semicolon. Okay, perfect. So now let's learn how to instantiate those beautiful half adder. So we need to put a name, and very so often I don't know what UUT refers to, but this is what I usually see. So UUT0 will be my first half adder. And we need to map the ports of that half adder that has just one AB and one SC to what input and or output and or signal it needs. Okay, so if I go back over here, the first adder will be connected. Where's my pen? Here. The first adder will be connected to A0, B0, so my inputs, but will also be connected on A XOR B and SC1. Okay, here. So let's do this. Whoops, here. Okay. So port map, and now I will take the name of the port of the half adder and map it to what input or signal or output I need it to be. And now it's easy because A and B of the first half adder are connected to A and B of the full adder. So A is mapped to A, B is mapped to B, and now the S, like I said, will be connected to S XOR B, because this is the output of the first half adder that will be connected to the A of the second half adder. So we have S will be connected to A XOR B, and the carry will be connected to SC1. Okay, in fact I should probably have put 0 and 1 here, but you know, I think you can a little bit understand how it works. Yo, Retro Gaming, how are you? Hope you have fun. All right, so now let's create the second half adder port map, and now the A connects to, so the A, the A here connects to this, and the B connects to CN. So this is what I need to do now. A S A XOR B. So B CN. S will be to the output S directly, and C will go to SC1. All right. So now all I've got to do is tell all I need to do is to tell that C out receive SC0 or SC1. All right. So this is the part over here. So this is C0, this is C1, C out is the OR of those two signals. All right. So if I were to ask a question that will answer myself, when this value A, B, and C change, A, B, and C change, are all of those entity change for all intents and purposes instantaneously? The answer is yes. It's not that the first half adder change and like 1 second or one clock cycle it change. There is a delay. Okay, so to be fair and to explain how it works, yes, there's a delay, but the delay is usually negligible. We will the only thing that delay will incur is that it will dictate how much fast we can compute the addition. Okay, so if I have, I don't know, a 10 nanoseconds delay, I cannot have a period of 10 nanoseconds because the time it propagates, I won't have the value. But for now, we don't need to go there. What we need to know is that those are executed or happen at the same time. Okay, water. Good. All right. So now we want to test our beautiful full adder. So how do we do this? We create a simulation. Create file. I will call it TB full adder. Okay. Here. Finished. Okay, so the test bench doesn't have any ports, but the component, I will copy the entity like I did for the half adder. So if I go to the full adder, I go at the top, take the entity part here, copy, go to the full adder. So you can imagine that when you change your code and you add new inputs, stuff like that, the pain is you literally cannot be dry with this. You need to copy paste and then go back to all the test benches and all the entities that import the first entity and modify the ports on each of them. So doing FPGA development in a agile manner won't really cut it, because the more the project grows, the more pollution and problem can arise, and you need to propagate a lot of code and duplicate it at a lot of places. All right, so I have my component here. I will need some signals. So what I will do is I will need a signal for each of my inputs and outputs, so I can see them in my simulation, and I will create a clock like I did earlier. The clock is just to follow like a cycle, change a value, and look that the value change. Okay, so let's do this. Signal SA, STD logic. Signal SB, STD logic. Signal SCN, STD logic. Signal SS, STD logic. So much fun. Whoops. Signal SC out, STD logic. What I can also do is set those three at the top at 0. So what it does is it just when you start simulation with STD logic and you don't initiating it is initiated at U. What it means is it is undefined and can cause a lot of problems. Those will be connected to output, so I won't be assigning values. The component will set those values. Okay, so now I need my constant. Oh damn, I don't like this. And I did some tests this week with Vivado, and for some reason at different time and for no apparent reason it decided just to crash. Like it just turned off. The application was closed and there were no signs of hanging, or I was like typing and everything seemed working correctly, and then paf, Vivado was crashing. So I don't know if you guys had any problem with that also. Okay, so period will be of type time, and we will set it to 10 nanoseconds, and we will need our CLK with VSD logic, and will be instantiated to 0. So the first thing I will do before doing my my component is just a process that will clock. That's end process. So wait for period divided by 2, because my clock needs to be rising, be, for instance, at the value 1 for half the period, then falling half the period, and so on. So the period needs to be divided by 2. Now SCLK will receive not SCLK. So the value of CLK will be the inverse of CLK. This will be a process that will work on its own, that is not dependent of what is going on after that. Okay? And here I will set my UUIT. It will be a full adder port map. A goes to SA. B goes to SB. C in goes to SCin. S goes to SS, and we have which SC out. C out goes to SC out. Good. Shouldn't be have any problem there. Let's go on. Okay. Now we will have the process that will actually do the testing, and we have 8 combination. So what I will do, and I know that I set them at 0 at the beginning, but just to be clear and concise, I will write all the value, the possible value, and that in that way there won't be any confusion when we read the code that we have 0, 1, 2, 3, 4 up to 7, because when you have 3 bits, we can represent 0, 1, 2, 3, 4, 5, 6, and 7 value. Okay, they are 8 value, but from 0 including to 7. Good. So let's do this. Wait for period. Now we will set SA those like, okay, no, I won't copy them. Just SA receive 0, SB receive 0, SC receive 0. And in fact, what I will do is put the wait for period at the end, like such. Good. SC in, sorry, like that. So let's copy this. 1, 2, 3, 4, 5, 6, 7, 8. Now we can, for instance, one here, one here, one here, one here, one here, one, and one, and we can just say wait at the end here, and what it does is it will eventually realize that we don't want it to do other stuff, but because what will happen is it will like loop forever, but by putting a wait there, it will stop earlier than if I just let it run ad finitatum. Ad finitatum. I'm inventing new words. Okay. So now I can run this test. So what I do is go to the TB full adder and set it as stop. So it will replace the half adder test bench as the main test. So when I run the simulation here, it's supposed to work properly. So does the demo god will work? Okay, did it work? So let's do this. It seems to have been working. Let's zoom in a little bit. Okay, so if we look at this, we have the C out here, so the carry, and we have the sum here, okay? If A, B, and C in are 0, everything is 0, perfect. If I have 1, I have a sum of 1, and the carry is still 0, perfect. Now I have 2 here, I will have 0 at the sum, and I will have 1 carry. Perfect. So far, so good. Let's go here. And the last one we need to look. So when all 3 are 1s, we have sum of 1, C out of 1s. So I'm pretty sure everything is working as intended. Perfect. Goodie. So our full adder is working. So now what we want to do is make a 16-bit full adder. So we will instantiate 16 of those full adder inside the entity, and instead of having a STD logic of 1 bit, we will create a bus of 16 bits, A and B, connect all of those wires correctly, and it should do the addition. So let's do this. We will go back to stream code like this, and we will go to source and create our design. Create file. Will be full adder 16. Okay. Finished. Now the full adder 16 doesn't have there is some things we need to be careful about. So A will be a bus of 16 bits, so it will start at 15 down to 0. So if we count 15 down to 0, each number including the 0, we have 16 wire. B will be the same thing, 15. Now I will put a C in here, but it will be a single wire. I could just ignore the C in there and not putting it, because if we think about it, our 16-bit adder will add 16-bit values. And if I go to the drawing board, like this, if I have this value, so this is 16 bits, okay? And if we could compute this, this is a this is the unit. This is 2, 4, 8, 16, 32, 64, 128, 256, etc. Okay, we could know the value, the numerical value of this this sequence. Just a moment. And I'm back. So if I want to add another value, you realize that this can be and those numbers that I will write are not doesn't really the number I will write won't be the value of those bits. But if I do 1344 plus 987, this will carry something. It will carry 1, but there is no, for now, in the context of these values, nothing can go in that carry here. All right, so I could ignore this. I could ignore the CN. The reason why I will put it in this first, like I will already put it there, is that in the future we will learn about 2's complement. That is a way to encode negative number so that we can use an adder to subtract. So in other words, we will use this Cin in conjunction with an inverter to compute a 2's complement and subtract values with the same circuit. And now you'll tell about what would you want to do that? What is the main goal? The main goal is simple. I will go back to the drawing board. Okay? There's a lot of things you need to consider when you do design. The design like on FPGA or like if you want to create an AC. What you have to remember is that you have a finite space. Space is finite. Okay? I hear you, some people are probably saying, hey Andrew, you can look at Cerebras, I think. They do a CPU that is big as a wafer. True. But do you think that if I have a big wafer with a lot of cores all around, do you think that this core here can communicate to this core as quickly as this one? Not really. So you have constraint in space. You have those constraints will have impact on timing, and also you have to decide what is important. Okay, so I could make a adder and a subtractor. This will take, let's say, this place and this place here. I lose this place cannot be used for instance, more L2 cache or more L3 cache. Okay, or I can make it just a tiny bit bigger, this one, and it will add a little bit complexity, but not that much. But that complexity will give me the possibility to have more cache on my L3 cache. So instead of having, I don't know, 1 meg of cache, I might be able to put 1.5 megabyte of cache. And for those who follow the AMD 3V cache and stuff like that, there are use cases where more cache is very beneficial. So for now, what I want you to understand is that designing has a lot of constraint, and those constraints have a lot of impact on speed and space and stuff like that. And you need to select what you want to prioritize. Okay. There's a reason why, for instance, AMD is able to put a lot of cores on a single die compared to Intel, but Intel has a lot of specialized modules, I would say, entities or IPs, like encoder, decoder, and stuff like that. And I'm talking about server grade CPUs, and in certain situation, even though the Intel has only 26 core compared to 64, or I think there's 96 cores EPIC CPUs nowadays, but even though there are so many cores in EPIC, there are some use cases where the Intel is better, because instead of optimizing their core and stuff like that, they use an architecture that facilitate adding other tools. And for instance, I think the Intel has a lot of accelerator for zip files, or encrypting, not encrypting, but the real term is compress. So they can there are some entities in the CPU that offload all the computation of zipping, dezipping stuff, so that it can do other work in the same time. And at the end of the day, they are more performant than AMD for that single task. Okay. So now we will have the sum, which will be an output and that output will be 16 bits. And the C out, but in fact we want the C out now, the carry has another meaning. We will still call it C out just to be thorough with our naming. Sorry for a moment. Okay, sorry. But in fact, we can consider it as an overflow. So 16 bits value can contain, I think it's 65,535, the biggest value. If for some reason we try to add a bunch of ones with a bunch of ones, of course it will overflow. And what it says is obviously the value that you're getting is not the right value because it's bigger than what a 16-bit address can hold. We would have need 17, for instance. Okay, and again, it will be only 1 bit, not a bus. We don't want to output all of the carries of each individual 16 carry. Okay, half adder, sorry, or full adder. So now we say okay, and we wait a second that it appears, and it's there. Good. So now the infamous full adder 16. Just getting my notes. I don't want to go on a limb. Is that this one? Yes, okay. Weird. I didn't put the right name. Where did I put this? No, not there. Okay. Okay, so what we will use is a new syntax that we didn't see. We will need our entity. So first of all, let's do a little copy paste here. Like such. Okay. So we will need to instantiate 16 of these full adder, and if we just think about it, the signal A here, you can imagine and see it as an array. So it's an array that starts. We can associate the 0th A to the first full adder, the one to the second, etc. And do the same thing with B, do the same thing with Cn, and so forth. What we will realize that S will the output will be mapped with all of the sum of each full adder, and only the last C out will go to the output. But we know that we will have one carry, one more carry than we will have other signals. Why? To the drawing board. Let's just draw a 4-bit adder. Okay. So we will have our first here full adder, A0, B0, and we will have the Cin that will go on that one. So, like I said, in the context of in the future, we will want to be able to do 2's complement. This will be ND. Now S0 here, and this is C. Like it's the C out 0. It will go into the C in here. A1, B1. 1, S1, C out 1 goes here. And we have A2, B2, S2, and the last one, sorry, it's a little cramped, A3, B3, like such. That is C out 2, and this go to C out, and this go to S3. Okay, so we have 1, 2, 3, 4, 5 carry signal that we will need to handle, but we have 4 A's, 4 B's, okay, and we have 4 S's. What we need to what we will do to simplify the code, we will create signals to map those carry, and we will call it carries. But what we S carries, sorry, and these, there will be, it will be not a, it will be a array of 5 in that context, because we have 4 bit in the context of our 16-bit. We will have 17. All right, so if we need 5, so what we do is 4 down to 0 here. Okay, and we will map Cin to the 0th, and then this one will map to the output of the first, and the input of the second. The output of the second will be the input of the third, and etc. Okay, so how do we write this? Let's go. Okay, so here, signal S carries, std logic vector, it will be 16 down to 0. So don't forget, it's 17 signals because we count the 0th. Okay, so we will use a generator, so gen, for, and you'll see on the internet, if you try to look at VHDL, some people use I, other use double I. I think the reason why some people use double I is that some people use I for some inputs some of the time. So I'm used to use the double I. You do what you want to do. Just a moment, please. Okay, so for double I, and if I remember correctly, just let me take my notes here. I don't find my for example. Where is it? No, not this one. Where is it? Did I put it there? I have too many files. Okay. Not that one. Okay, let me check here for a second. Okay, so okay, yes. So the structure of a for generate in VHDL is you need to set the range. So in, and I will, we know that we have 16 half adders, so 0 to 15, generate. And now we will do the end generate, and we can use the same name over there. Okay. So now I will need to do some arithmetics, and when you do some arithmetics, you will need to import a new library, and I didn't really explain how those library works. So let me explain a little bit. So triple E is the it's a, I think, American Engineering Association. It's the association in the United States, and I would guess probably a lot of other organization in the world tries to follow the same ruling. So if you, for instance, if you do something in Canada and you follow the engineering of your province, for instance, so the guidelines that you follow will probably be the accepted in the United States. So if you sign something on a design like for a bridge or whatever, it will be considered compliant, of course, if you did your job correctly. So now those are giving libraries that are like in the visual standard, I guess. And STD Logic 1164 gives us STD Logic and STD Logic Vector. And those two type of signals, so STD Logic are, like it says, a wire, and vector, they are vectors of wires. So they can have different values. So they can be undefined, they can be high impedance, they can be 0, they can be 1. I think there are other value it can take. And if you want to handle integers, so I don't know if you saw, but when I instantiate, like in my full adder test, my 0 is not 0 here. I don't put it at 0 because 0 is an integer, but single quote 0 single quote, it represents the 0 value, logical 0 value. Okay, so now that I want to use integer and handle integers, what I will do is import what is called the EEE dot numeric std. I don't choose the name, guys. Okay, so don't attack me on this. Okay, so see, it's for numeric standard, and so numeric standard will give us, and it's written in the comment here. Gives us a lot of function and tools to handle and manipulate and do work on the integer. And after we have finished with it, we can convert it back, if we need to, into a STD logic vector. Okay, so what I need to do here is create UUTs, and those will be full adder, like this here, port map. And now what I need to say, so the A will be equal to AII, so the first wire in the 16 wires that A received, the first wire will go into the first, the second into the second, etc. Same thing for B. BII. Now, this is where it gets a little tricky. Cin will receive S carries II, because at the end, in the process, S carries 0 will receive Cin. And the only reason why I do this is because I don't want to make a special case when II is 0. Okay, so it's just to make it easier. Now I need S to be SII, and just make some more place. C out will be S carries II plus 1. Okay, so like we saw earlier here, these signals go into the next one, and everything will be will be offset of 1 because the 0 is the C in. So if II is 0, the 0 will be the C in, the 1 will be the C out. And when I come back into my code here, the I, when it goes to 1, so it takes 1 as C in, so the 1 was the C out of the previous one, and is now the C in of the current one. Okay? And is there anything left? Yes, what I need to say now is C out will receive S carries 16. Is that right? Yeah, it's the last one. Okay. Like such. Good. Okay. So if I go here, let's just make our life a little easier. I think we can see it. There's not much comment right now. If I look at the other 16-bit, look at all of those gen 0, 1, 2, 3, 4, 5, up to 15. And those are all full adders. All right? So what you need to know is that when I generate here, the for loop that I generated here, it's not a for loop like in C. Again, these are circuit design. Okay? Those are definition of 16 full adder that are interconnected. And yes, the propagation delay will be longer since the last full adder will receive the carry of the previous one after the previous one, etc. But for all intended purposes and for the small place it will take, we can consider it as instantaneous. Okay? So all of this will go as fast as before. Okay. So I'm now at the point where we need to do the test bench. I will just take a few moments to go to the bathroom, and I'll be back in like a minute or two. And I'm back. Okay. So for those who are listening, we have created a new entity. The next step would be we need a test bench to make sure it works properly. So now there are a lot of ways we could do this, and 16 bits, like I said, it goes into the 65. In fact, it's 64K in terms of value it can hold. So testing everything like we did would be a real pain. So for instance, when we did the full adder, you remember that the test bench, sorry, here, full adder, test bench, here. Okay, when we used the it was easy to do the 8 different combination. Okay, it's not that hard, but we can have 65,000 values in A, 65,000 values in B, so it's like over 100,000 combination. It's and more, in fact. So it can be very hard to test everything. So what we will do is we will try some values at first, and then try to find a way that we could do more. Okay. So let's create a new simulation. Simulation here. Next, create a file. TB full adder 16. Finished. No ports. Yes. And let's do it. Okay, so here we will need the full adder 16. So we copy this and this component. So fun. I like this. Really, I'm so happy. All right. We will need the signals. It will be pretty much the same ones as here, but what we will need to do is change some into SED logic vectors like this. Oh. Ah, what did I do? Okay. Console. Let's copy back this. Like this. Okay. So the A will be a vector, the B will be a vector, and the S will be a vector. They will be all 16 bits. And now I will show you three ways to instantiate a SD vector. So one is all bits. So, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Boom. So this is one of the way we can instantiate 16-bit at 0. We could place an X. So now each 0 counts for 4 bits. So we can do this that way. And the other way we can do is, this is probably the one I see on the internet that is the most used in what I found, is this construct. So what happens here is that when you have value to assign, you can specify which one you want to have a certain value, and then for instance, let's say that there is 16 places and you want to set certain value to 1 and all the others to 0. So you will use that construct to set which one you want to 1 and others equal 0. So and when you have arrays also, so what I mean is like matrices, you will do stuff like others will lead to others to be 0. Okay, stuff like that. So now we need to connect all our marvelous signals. So A goes to SA, B goes to SB. Damn, with my I have so many thumbs. CIN goes to SCIN, S goes to SS, and Cout goes to SCout. I think I'm okay. What's the problem? Expected an architecture identifier. Oh, port map. Alright, I think this is perfect. Okay, now what do we need? The clock. So let's go back here. Let's copy this, put it in there, and we have a clock. Great. And the last thing we will need is to try some combination of values. So let's try to make I don't know, like eight combination like we did with the previous one. So we need a process. Begin and process. So first of all, let's just copy the this. But now what we will do is let's say everything is at 0, like this, and it's at 0. Now 1, 2, 3, 4, 5, 6, 7, 8. Let's put five A, and here 1, 1, 1, 1. Here, let's say DEAD, BEEF. Here, let's try 1337 and 0042. 0408. 15, 16, 21, 42, ABCD, FFFF, 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 R. Alright, so if we just try to figure out what would happen, so here it's 0, Cout will be 0. This will lead probably to no overflow in Cout, and B6 I would presume. Then it might overflow. I'm not sure if it will overflow because no, I don't think it will overflow this, but this two here will overflow. That's for sure. And so let's see if everything's works. So we will set this test bench as top. And it's done. Now let's try to, oh yeah, I need to add a wait at the end here. Sorry about that. Like such. Okay. I will try something. I found some tools in the chat, and I want just to try to put a marker because I would like at some point to make how can I say, I would like to make a short or stuff like that, or highlights, and marker would be helpful. So if I try this and just make test bench full adder 60, just want to see what it will do. Okay, so we added a stream marker. Perfect. Good. Let's see. There's other stuff I would try. Probably try the the read command at the end of the stream. I would have liked to do it last week, but unfortunately I wasn't ready. Okay, so we are ready to simulate. So let's do this. Oh, there's a problem. Cannot access because it is used by another process. So this happened a lot lately. So what I needed to do. So if I try to run it again, what you'll see is that there is a file that seems to be used by someone else. And if I go in Teckle, I will see that path here. So if I copy this and paste it here, I will find that file here. If I try to delete it, it will say the same thing. Windows is not able to like free something didn't free the file. Okay, so for those who do C or C++, someone messed up and didn't call the close on the file. So now what I do usually is I will turn off Vivado, so I will close it completely and close this also. What I will do is start Task Manager like this and try to see there is a Vivado still hanging out by the threads. So I go down, and it doesn't seem we have a Vivado somewhere. So it looks okay. To be sure, what I will do is go back into this, copy, try to delete it, and now it works. So perfect. I can restart it. If I'm telling you, it happens sometimes that there is a thread that is not in the upper part. So here, those are threads that those threads are apps that usually has GUI open. Okay, so I close Vivado. So usually there is no Vivado here, but sometimes there is a thread or process that was started independently, and that process don't die, and this one holds like the rights or the pointer to the file. So now I can close this. We go back in start Vivado. That's fun. Okay, now let's try to run the simulation. Okay, so now let's go over there and zoom a little. Okay, so now what do we see? 0, 0 equals 0. That's right. 5A, 1, 1, 1, 1, 6B, 6B. That's right. That beef. So the SC out is at 0 at that beef. No, it's our. So it's that addition overflowed. In fact, we see it. The value is 9D9C. So since 9 is clearly less than DRB, we overflow. So this one didn't overflow. Let's just go one by one. This one didn't overflow. So here we have FF, FF plus FF. We remember that SA didn't change in both of those situations. So FFFE, so it overflow at the maximum. And here it overflow, but the value is 0. Why? Because FFFF, it's all ones plus ones. Everything becomes zeros except the overflow. The only way to not overflow with FFFF is if I add 0. So our adder seems to work. Okay. I will not tonight. I will not show you how we could create a instead of for generate, we can create a for loop in the test bench to literally simulate all combination possible. Like I said, it's there is 65,000 combination that can be associated to 65,000. So the number is astronomical. It's like in 4 million different permutation. So the test can be written, it could be run, and there is stuff we could do, like we could put asserts into the test and say, I expect that value to be that operation. We expect that value, so we could run it like for, I don't know, days, and be sure it passed all the tests. Okay, but I won't do this tonight because I would like to go back and try to figure out how we will use this to multiply two 8 bits values. So we, instead of having 16 bits, we have two 8 bits that we want to multiply, and we will see soon enough that multiplying values in binary will like the number of bits total you have will be the total number of bits you will need to hold those values. So I will need to go to the drawing board. I will go over here and let's put a marker there. So explaining multiplication in binary. Okay, good. Let's move the mic near the new page. Okay, so you might hear my little cat is being taken care of, needs some attention. Okay, just a second, I'll be back in a few seconds. It's important to hydrate. Okay, so when I multiply decimal values, okay, so let's say 356 times 200, no, let's take something bigger, 703. Okay, what happens is I will multiply all of these numbers here, then it will give me a number of units I have. After that, I will multiply those here, but this will give me tens, and same thing with this, it will give me hundreds. Okay, so let's do this. So 618 carry 1, 15 plus 1, 16, 9, 10. Good. Now I will draw a 0. Let's just, for the sake of simplicity, remove those carries, and it's pretty easy. Those are all zeros. Perfect. Let's put 2 zeros. Now, oh wait, just remove those arrows. It will be a cluster F. Okay, so now I need 2 zeros here. So 7 times 6 is 42, I guess. Is it that? 7 times 7 is 49. Yeah, so 42, 4. 35 plus 4, 39. 3. 21 plus 4, 3, 24. All right. So now what you can see is that all those values will be added up. Okay. So 8, 0, 0, 8, 6, 0, 0, 6, 0, 0, 2, 2, 1 0 9 0 carry 1 4 1 5 2. So at the end, the possibility is that I will have double the number of digits that I add. It's not a double, in fact. If we look, I have 3 digits here, 3 digits here. I end up with 6, and it makes sense because if I have 1,000 times 1,000, or like 1,000 times 9999, we know that this correlates to 9999 with 3 zeros. Okay, so at most we will have the same number of digits we have, or one less. In that situation, we have one less. Okay. There's not much difference in binary. So let's take the value 18. Okay, so 18, we need 16, 0, 8, 4, 2, 0. So this is 18. Why? This is 1, this is 2, this is 4, this is 8, 16. 16 plus 2 equals 18. Okay? And I want to multiply by 5. So 0, 0, 1, 0, 1. Okay, so it's simple. I will remove those 0 for convenience. So what is no, let's say we want 7, just to see a more complete example. So when we are binary, it's very easy when we do stuff like multiplication, because if I have a 1, what does it mean? It means that all of this will be copied back at the same place. Okay, so when I say same place, this is units, so these will be units. These are power of 2, so 2 to the power of 2, so this will be put with a 0 there, and this will with a 0 there. Okay, so since I have 1, it will be 1 0 0 1 0. I have a 1 0 and 0 0 1. I have a 1 1 2 3 1 0 0 1. Now I add everything. 0 1 1 1, and this is funny. It's all ones, except the first one. Is it right? What are the chances? Like, is there something not well aligned? 0 0. Okay, wow, perfect. So what we see is that if you see that I will need to add I will need to add a certain number of times each time there is a 1 in. So this is A, this is B. Each time B has a 1 at a certain place, I will shift A, the number at the place I am in B, and add to the value I'm currently at. So this is what I called, and I talked about it last week, multiply and accumulate. Multiply and accumulate. Okay. So in that context, in concept of binary, it's very easy to multiply by 1. By 0, we just don't do anything, and by 1, we take the value we add. All right. So, like I said, the worst case scenario we have is that A is some number. So, for instance, I don't know, maybe 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1 0 1. So this is 5, and B is 1 1. Sorry, it's 8-bit. I think I started to be a little bit tired. Okay, so 8-bit and 1 1 1 1 1 1 1. Okay, so what does it mean? It means that I will shift this 8 times. Okay, so the first time we will have for sake of convenience, only 101. At the second time, we will have 0101, that is 10. 3, we have 01010, that is 20. 101000, 40, etc. And those, if we do this 8 times, what will happen is that we will have 1010, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the worst case scenario is that we need all ones. Okay, so if we have all ones and we move this 8 times, I need to keep track of 16 bits. So this is why I needed a 16-bit adder for 8x8 multiplier. Okay, needs 16-bit. So, and maybe you realize that it's possible that it's easy to overflow in that context, and that is not the problem we want to solve right now. What we want to solve is just given 8-bit numbers, and I want to multiply it by another 8-bit numbers. What do I need? I need the minimum of 16 bits. Okay. All right. So how do we approach this? So, so far, except in test bench, we didn't use the clock. Okay, so no clock in the half adder, no clock in the full adder, nor in the 16-bit full adder. Why? Because we didn't need it. But now we have a problem. What we want is that we want to first, we will receive 2 values, each 8 bits. Then what we want to do is like we will identify the ID A and B. So one of those values will be A, the other one will be B, and you realize that either way it will be the either of these values could be A or B. It will change the value at the end because multiplication is associative. I will say hello to Cerebral Wall Z. How are you, guy? Okay, after we have identified A and B, let's say that A will be the one shifted, and B will be used to define when it's 1 we do something and 0 do nothing. Yeah, you can ask Chowie, you can ask any question you want. I might not be able to answer it very efficiently. I'm not that an expert. For those who just came for the first time in sorry. For you guys who are coming first, I'm a student doing my master degrees in electrical engineering, but in reality it's just computer science. There is no computer science master in Canada for what I know. So the title is electrical, but I'm very interested in low level design like that. So I'm working on some project in VHDL in robotics as about now, and I'm learning a lot of the stuff like clock constraint and different kind of things like that. You work for FPGA tools. Want to see Yeah, but I would love to see more people doing FPGA because it's very interesting. And yes, the cost of entry is high, but I think it's worth it. Last undergrad in electrical and computer engineering, and I really like learning about Verilog FPGA. I think that very soon I will try Verilog. VGL, there's some stuff that I don't like. It's a very old language, so yeah, that's pretty cool. So if you have any question, just throw it. I might not see them right away, but I will try to answer quickly. Okay, so the first step, like I said, is to sorry, I will bring the microphone. Is to receive two values. Each of them will be 8 bits, and one of those value I will shift, and the B value that I'm currently looking at. So if I'm looking at the to the power of 0 to the power of 1, the value of the bits in the bus will decide if I do something. So if it's a 1, I will add the value of A shifted, and if it's 0, I just do nothing. Okay, so let's say do point 2, look if bi equal 1, then shift A by E and accumulate. So when we see stuff like accumulate, what it means is that at some point somewhere I'll need probably a register to hold that information. Okay, so I will need first a something that will give me the opportunity to shift A. Okay, and there is other step here, but I will tackle this problem first, the shift register. Okay, shift register 16. Okay, this module will receive let's say for yeah, okay, I will do it like this. We will need some values to help the register to do its job. So the first thing we will need to do is to set it at the initial value. Okay, so like the A, I will draw it better, sorry about that. The A signal will be 8 bit. Okay, and we will have a signal here that will be called load. That means that at that point we will set the register to the 8 bit we receive in A. Okay, then we will have another signal here, clock, and we'll be probably have something like a signal that means we start shifting. Okay, so let's call it start for our needs. Okay, so what will happen is if starts it's 0, nothing really happens, because and load also needs to be 0. The shift register does nothing. Even if the clock oscillates, nothing will happen in the shift register. The shift register will output a value just on 16 bits. Okay. There's a lot of the main issue with the video tool is how close. So yeah, it's that is one of the thing I find hard. Like Vivado is okay for what I know about it. I know that I'm not using it like really properly. Most of the people that I know use like Tickle script to generate and don't really use the IDE. But I saw that some company sells software at like $19,000 the license to be able to do crazy stuff and like do this is so expensive. Um, Depends on dev kits are also pretty expensive. Um, like you mean like this one, the one I use. I don't know if I show you guys. So the one I'm using for the stream is the Arty Z7. It's a ZenQ Z7-20, so it's not big. Like it's okay, bigger than the Z7-10, but it has two ARM core along with the FPGA fabric, and this board cost me with I bought it with this P mode here that holds a Bluetooth antenna, and also this little OLED screen, P mode also. All of this cost me like 500 Canadian dollars, so I don't know, maybe 300. And I'm currently giving a class at my university for a project they have to do for all semester. It's their fourth terms in computer science, and they use the Zibo. It's very similar to the RT, the same company. There's a lot more P mode. Sorry, I cannot really display it correctly. The ARM CPU are a little faster in this one, but this is the Z710, a little bit a little less powerful in terms of there's less FPGA fabric compared to the Arty Z7-20, but this one is almost the same price because there are a lot of connectivity that the RT doesn't have. The RT have a Arduino shell that can be interesting, but I didn't really look it up that much. So $500, it's not free, of course, but yeah, I see that some people could find it's not like an Arduino that is like, I don't know, I don't even know the price of an Arduino, but a Raspberry Pi that is a full-fledged computer, it's like $100 Canadian, about 120, so it's not the same thing. Does this have an HPS? What is an HPS? Let me look this up. HPS. Bridge. Hard processor system. It looks like if I do a research, it gives me Intel. But is this available for good question. Like, sorry, just a second, I will be back in like in 1 minute. Okay, I'm back. Good. Okay, so I saw that I know that Altera stuff has HPS CPU built into their most newer stuff. So I'm not sure if that is what you mean, but the FPGA here, this one has 2 ARM core. So if I go back into the screen here and like open the block design here, and just so you can see, this is the ZenQ processing system, and you will see that there is 2 ARM Cortex A9. Those are clocked at 650 megahertz. Though they are ARM V7 architecture. You can see the cache and all of that big good stuff, and you can see all of the different interface as for peripheral and also the AXC. So ARM uses AXC bus for intercommunication between and the FPGA fabric and other component we would need. So I don't know if this is what you're talking about, but yeah, Xilinx has this FPGA here, both of them, the RT and the Zibo, as ARM CPU, and they can run a version of Linux. It's called Pita Linux. Never tried it yet. You have like to select what you need, and then there's a part to compile, but you can run a Linux and connect to it. I'll probably try it very soon. Okay. Yeah, of course. No, the I don't compare a Raspberry Pi with FPGA. They are very different beasts, and but what I meant is that the price of entry is very different. And what I understand is that an FPGA fabric is mainly basically a lot of RAM memory, but with when we say fabric, there is an interconnect that we can activate some with which flip flop is activated will like draw the circuit you want. So, but yeah, when you what I mean is that when I don't remember who said that. Like it's not very easy to enter that market. And I saw earlier today someone on Reddit talk about buying like a pretty decent FPGA that you could put in your computer. And what you need to know is that when you buy expensive FPGA that has a lot of IP feature in it, those IP you need to pay again. So I don't have any example because I didn't use them, but I would assume that if you want some kind of accelerator activated, you will need Invivado to pay those through a license, and they can be very expensive as well because there's a lot of know-how. If you look at this, I'm very happy. AMD gives me the possibility to play with this component, but there's a lot of code behind this. There's a lot of stuff that they had to do, and they gave it for free. Okay, so for my FPGA, I can control everything on my CPU and my FPGA. But at a certain point, they say, if you can pay $5,000 for FPGA, you can give me $2, $3, $4, $5,000 more for the license, and the price explode in that way. So you can flash on Linux into it, but yes, Beta Linux. I didn't try it yet, but probably try it at some point. and of course, documentation seems to be abysmal, at least. All right, okay. So let's get back to the shift register I was thinking earlier. So what I want to do is. Okay, do you hear me? Yes? Okay, perfect. Sorry about that. I unfortunately moved my microphone to be able to draw, and it disconnected my microphone. All right. Okay, back to business. So we will have a 8-bit input that will set the initial value of the register when the load will be activated to 1. So it will be a active high. And so what we will need to do is hold the load at 1 up until the clock signal is rising. So at the moment it's rising, we will be able to put the load at 0. And then after that, once the value is loaded, when we hatch the start to 1 and keep it at 1, see at each rising clock, we will shift the register by 1 to the left, and this will be outputted in this V output that is 16 bits. Okay, so this module will do that job over there. Okay, so let's do this. Let's go back here. Right, I think I need to be very careful with the microphone. We go back to sources, and we will add a new design. This will be called Shift Register 16. Finished. Sorry about that. So we will have A. That is it will be 8 bits. We will have a load. That is just a signal. We said we will have a clock. That is a signal, and we will have a start. That will be a signal as well. And the output, we call it V. I know the naming scheme is not ideal, but for now we will go with it. That is 16 bits. All right. So, okay. We wait that it open over there, and we are now ready to work that. And so we will learn. We didn't use the like. There's a way to sorry about my expression. Concatenate. Did it go again? It didn't went out again. Okay, it's a previous message. Sorry. Okay. What we want is, like I said, when the rising edge of the clock is true and load is 1, we want to set a register inside our shift register to the value of A with leading zeros. There will be 8 leading zeros and the 8 bits of A. So if I just do this expression without thinking about any signals or whatever, so I will put a signal reg 16. That is a logic vector 15 down to 0. That I will need, and I will set it to 0. Yes, just go this way. Sorry about that. Others 0. Okay, so this has been instantiated as 0. So if I just want to say take A and put it in reg 16 with 8 leading 0, how do I do that? It's just reg 16 receive 1 2 3 4 5 6 7 8 and A. Okay, so what happened is, this is not the binary AND you are used to in C. In C, if I do something like this, what it does is it will take A, take each bit of this expression, and compare bit by bit with A. Okay, this is not what is happening here. This is a bit concatenation. Okay, but now I don't want this to happen every time. I want this to happen only when clock is high, so while it's rising, and when load is 1. So how do I do that? I need a process that will look at the clock, the load, and what we do, begin, end process. What do we do? So if rising edge of clock and load equal 1, then end if. Okay, so right now the only thing our shift register does is it's looking if the clock is rising, and if it's rising and the load is 1, then set the reg 16 to 8 zeros, leave these zeros with and the A appended. Okay? So that's great. Oh, I need a semicolon here. Good. So now if the start is on, so if the start is 1, I want to shift it at the rising edge also. Okay, so I can do else if here and look closely to how I'll write else if. It's one of the worst way I have seen. I think there is elif I see also in some language. I don't remember which one, but this is like really easy to me. So else if, no E, no space. And I want to say that rising edge CLK and start equal 1. Then, and at that point, the only thing I want to do is reg 16 will get reg 16, and I take the 15 last bits. So I ignore the most significant bit. I take the 15th to the 0th, and I append a 0. Okay, so basically what happened is that if I have 1 0 0 1 0 0 1 0 1 0 1 0 0 1 0 1, so 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Okay, so what I do is I take all of this and put a 0, so this will disappear and this will appear. Okay, great. So like as of right now, one of the things that will that could happen is that we could ask some question to ourselves and say, hey, what will happen if load and start are equal to 1? Okay, and that could be problematic. So how can we be sure that there's no like shortcut or anything? We can just add load equal 0 here. So what it does is the only way to go so I start over. What I've just said is completely useless because it's an if statement. So if this is true, it will do this, and if it's not true, it will do this. So there won't be any problem with load and start being 1. Load will win at that point, so it won't shift anything. Okay, great. So what do we do now that we have a entity we need to test? So we create a test bench. So let's do this. Click on the plus, create simulation, create a file, tb shift register 16. Oh, there's something missing. I will just finish this, say okay, yes. So now what's missing is that I didn't connect with 16 to the V. So just here, V gets reg 16. Good. Okay, now we are ready to test. I will take a sip of water. All right, so earlier I said to you guys that the one of the things I didn't like with VHDL is that there's some quirks that I don't really understand, and one of these is that if I want to use an entity, I need to copy that entity as a component. So here I need to copy this code, put it in my test bench, and if I was to use this shift register into another entity, I would copy there too. So I could I could end up with a lot of entities using a lot of entities. And those entities, if I change one of them, I need to backtrack all of the dependent entities that use it. And I hope that Verilog doesn't do that thing. It's like I like to compare it like if I was to code in C++ and create a class, and I have another class that uses that class that like as inheritance or composition, anything I want, and I would need to copy the header file into the other class because it needs to know how it works. So this is something I found very annoying. Okay, so what do we need to do? Create our shift register port map. Before that, I need some signals to follow in my simulation. So SA, it will be this. Signal sload, std logic. Signal the sclk, std logic. Signal start, std logic again. And we will have signal SV, std like such. Okay. And I will need, if I go back to, for instance, my full adder, I will just copy this here. And let's copy this here. So what it does, it's a process that for every half a period switch the CLK value. So let's put this after here, and now we are ready. So we will set A as SA, load as sload, CLK as CLK, SCLK, sorry. Start will receive as start, and V will receive as V. Okay, so I guess this is correct. So I want to go back to a concept I talked earlier. So shift register as something different compared like the full adder. Okay, so the full adder, like I said, for all intent and purposes, everything happened at once. Okay, it's not really true. There is some progression delay, but it's not dependent of a clock. So we call this a combinatory circuit. Okay, we'll design something like that. When we play with the shift register, now considering the clock state, then we do something. So now we are in sequential design. So sequential, obviously, it's not. It means that I won't be able to do something in a single clock cycle. Okay, it will take some cycle to do something. So when I take, for instance, a x86 processor that tries to multiply two 32-bit or divide two 32-bit values, it can take hundreds of cycles of the CPU to achieve that task. And there are ways to optimize this, but the CPU doesn't optimize this because it's not its job. Its job is to give functionality that covers a lot of range of problems. Okay, so the shift register we are doing here, shift register exists and they are used at very kind of in various situations. But the multiplicator we will do might not be the most optimal one. There are probably other way to do this. Okay, so now let's test this sequential circuit. Okay, where is my test bench? Oh, over there. V shift register. Okay, so now we need a process for the tests. So begin end process. Okay, so one of the things I will do is set SA load for a clock cycle, then set load to 0, and make sure that the value that I get at the output is what I set in SA. Okay, so we just do that for now. So and before that we will set this to 0. This to 0. This to 0. And this to 0. Okay. This will be a output, so we don't set it any value for now. And so wait for period. Then we will set SA to this value, so it's 5A, and set load to 1, wait for period, S load to 0. So what we should see is for a period there might be no value or undefined value at the output V. Maybe not, because we set the value of the register to 0. We instantiate it at 0, so probably 0. Then when we set load to 1 with the 5A in SA, we will get that at the output after the rising of the clock. And when the load goes down, the value should stay the same. So let's try this. We need to put our shift register as a top design. So this is done, and now let's try to run simulation. Yeah, that's what I thought. So if I close this, okay, so again the same problem we had earlier. So what I do is usually I just close Vivado, look if all Vivado process has been killed. Whoa. Yes, I guess everything is killed. So let's restart Vivado. It's loading. Arty fun. So much fun. Okay, now let's run simulation again. So I think I forgot to put the wait at the end, but I don't think it will be that much of a problem. Let's go back here and zoom a little bit. Okay, so we see that SA here is 0 for 1 cycle. Oh, 1 cycle is 0. Then we set 5A in SA and load at 1. So at the rising edge here of the clock, we see that the register and SV has changed to the value we wanted. Then when we drop the load, there's no change in the value inside SV. So for all the rest of the simulation, everything stays the same. Okay, so now what I want to do is activate the start for 8 periods, and what we should see is 5A should change value depending of how many rising edge we had. So we go back to here. We open we sorry about that, I was distracted. Okay, we open the simulation. So let's shift here. And now we will add wait for period, start receive 1, wait for periods time 8, start receive 0, and what we should see is at the first we will have this will become 0 1 1 1 0 1 0 1 0 0, sorry. Then after that 0 1 0 1 1 0 1 0 0 0, etc. Okay. So let's try this. I will just hide the chat for a second since we want to see the simulation. So let's rerun this. Yes. Okay. Oh, I think it worked. Yeah. So let's zoom this and go back in that zone and zoom a little bit. Okay. So we see that at the moment here we set the start to 0, to 1, sorry. At the rising edge it becomes P4. So it makes sense because if we look, let's take paint for that, it will be a little bit quicker. So if I have 0 1 0 1 1 0 1 0, so this is 5A, and I add a 0 here. Okay, so now the 4-bit LSB, so the less significant bits, is 0 1 0 0, so this is 4. And now this here is the 4 bits MSB, but not really because it's 16 bits. So there are a lot of 0 over there. We don't see them in the simulation at that point. Oh no, we see them. They are there. 0 0 here. So this, like I said, 0 1 0 1 is A. So if I add 1, it's a B. Like such. So for what I understand, if I add a 0 here again, now this one will go in the next 4 bits, and so there's a 1 here, 6 8, and don't have to look at that much, but pretty sure it works as intended. So if we look, there's 1 2 3 4 5 6 7 8, and it ends. So our shift register is working as intended for now. That's good. So this would probably be the end of the stream for tonight, since it's already 11 for me. I don't think we will have time to start. The next step would be to create the controller, and then the controller will be able to, when I want to start a multiplication, control the register, control the 16-bit adder and stuff like that, to be able to do the multiplication. So this will probably be next week. So I don't know how many people are still there, but I might try the rate command. So if you want, I will try to find something interesting. So let's go to Twitch, browse, let's go to creative, and then software here. And so we have Via Lorraine, that is the I think, no, it's not the most popular. There L colon Q here that don't know what is doing. Yeah, good night to you, Kanda Vegeta. So I guess it's a reference to I don't remember the name. I have such a bad memory for names. Unreal Engine, free open source feature, flagging, Min.io, Game Boy in Lisp. Lisp. Okay, I guess I will try to rate this one. What do you think, guys? So raid, I guess it's LCOLQ. So is intended to mature. Oh, it's intended to mature audience. Okay, so you've been warned. Right now.